Hey Professor, I'm going to give a talk on the Spinning Projectile Extreme Environment Robot, also known as the SPEAR. So recently these things called skylights were discovered on the Moon and Mars. They're pictured there on the right. Unfortunately, they're occluded and you can't really see inside them from satellites. So I wanted to build a robot that could see inside. And so the top level goal was to design a low-cost, compact, disposable microbot to explore these skylights, which I called the SPEAR. This is the concept of operations for the Spear. Essentially, you have a launcher and the Spear itself mounted onto a rover, and you catapult the Spear into the pit. And then just before impact, a little rocket motor inside the Spear ignites for a soft touchdown so it doesn't crash. And so this utilizes something I created called two-axis spin stabilization instead of a reaction control system. The reasoning for this is reaction control systems are heavy and bulky, especially for something that can be very small. The questions I wanted to ask are as follows. Would the dynamics of such a system be feasible? How about practical? And also, can we take panoramic photos from the rapidly tumbling Spear? And that requires some state estimation. So this is how the rest of the talk is going to look. I'm going to talk about mechanical design, electrical design, analytical dynamics, numerical dynamics, visual state estimation, then image reconstruction for the panoramas, and then finally the results for the dynamics and the results for the vision. So this is the mechanical design. You can see it has a 5 centimeter radius. It's a sphere. The chassis and components I designed using SolidWorks, and then we use SLA 3D printing to actually print the chassis and some of the brackets. This is the exploded design of the spear, just so you can see all the different pieces. You can see that altogether the thing just weighs just under half a kilogram. This is a circuitry design. So I designed this and I put it together myself. And so we have to worry about power and data for the IMU, the computer, the motor ignition system, the camera, and of course the power supply. I modeled the dynamics in two different ways. The first way, I used simplifying assumptions so that we could get an analytical model. So you can see in orange and red the simplifying assumptions. And then I also put together a numerical dynamics model that did not make those same assumptions here. So you can see the orange and red boxes now no longer make those assumptions. So this is more of a complete rigid body simulation. So I wanted to do a state estimate using the motion blur caused by the tumbling of the camera as the spear tumbles around. And so the way this works is you have these linear streaks from point light sources. And so using that, you can actually calculate an estimate of your state. And then once you have the state estimate, you can start doing things like generating panoramas. You can correct for various image effects like rolling shutter and blur. Now I'm going to go in and discuss the results. So here we compared our analytical and numerical dynamics models. And you can see that the analytical model very closely tracks the numerical model, and the analytical model is much faster and easier to solve, so we can use that for most of the dynamics. We wanted to see if this thing worked in the real world too, so we decided to do a real world test. I went ahead and built and put together the system. Then I went out and tested it in the Arizona desert. Slow motion. In the video, it's a bit hard to tell what's going on, so here are some of the frames from that video. You can see it does a nice few rotations before it settles gently in the net. And so comparing the experimental results to our numerical results, you can see that they're pretty close, about 1 meter a second off. And so these real-world tests show that our simulations are accurate. We went ahead and did a separate test to evaluate the accuracy of our visual state estimation system. So here we're actually not using any IMU data, it's just from the camera. And you can see that the direction of the tumble is very close to the actual tumble, and our spin rate is also very close to the true spin rate. And so with those state estimates, you can see we can take these super blurry, incomprehensible images, and we turn this into a human readable output image that closely matches the ground truth.